This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on optimizing functions of two variables and classifying those as minimums, maximums, and saddle points. So just shortcutting that as min, max, saddle for functions of two variables. So we have a function f of xy is 2x cubed plus 2y cubed minus 24xy plus 7. We want to find all the critical points and classify each of those as a minimum, a maximum, or a saddle point. So to find the critical points, we're going to need to find the partial derivatives with respect to x and y and set them equal to 0. So there's our function. We first want the partial derivative of f with respect to x. The partial with respect to x of the first piece plus the partial with respect to x of the second piece minus the partial with respect to x of the third piece plus the partial with respect to x of 7. Remember, if it's a partial with respect to x, any function of y is perceived as a constant. 2y cubed is a function of y that's perceived as a constant. The derivative would be 0. The partial with respect to x of 7 is also 0 because 7 is a constant. But I can pull the 2 out in front here to take 2 times the partial of x cubed. And I can pull 24y out here because y is perceived as a constant. 24 is a constant. I can pull those out in front of the partial derivative operator. So you'll notice 2 times the partial of x cubed plus 0 minus 24y times the partial with respect to x of x plus 0. Once I just have one variable, the partial derivative is the same as the derivative, so this will be 3x squared and this will be 1. So 2 times 3x squared minus 24y times 1, which will give me an f sub x of 6x squared minus 24y. That is the partial derivative with respect to x. We're going to need to set that equal to 0. We also need to take the partial derivative with respect to y and set that equal to 0. So here's our function. F sub y is the partial with respect to y of the first piece plus the partial with respect to y of the second piece minus the partial with respect to y of the third piece plus the partial with respect to y of the fourth piece. Now, in this case, x is perceived as a constant, so the partial of y of 2x cubed is just going to be 0. We'll pull the 2 out in front here. We'll pull the 24x out in front here because 24 is a constant. X is perceived as a constant. The partial with respect to y of 7 is just 0 because 7 is a constant. So now once I've pulled everything out, these partial derivatives are the same as regular derivatives. The derivative with respect to y of y cubed is 3y squared, so 2 times 3y squared. The partial with respect to y of y is 1, so 2 times 3y squared minus 24x times 1, which of course is going to give me 6y squared minus 24x. So we have the two partials. We need to set them both equal to 0 and solve for the critical points. So we have f sub x is 6x squared minus 24y, f sub y is 6y squared minus 24x. Set them both equal to 0. I'll start with this one. So 0 is 6x squared minus 24y. Adding 24y to both sides, we get 24y is 6x squared. Dividing by 24, 6x squared over 24, but of course 6 over 24 reduces to 1 over 4. So now I have y is equal to x squared over 4, and I can make the substitution in this equation. We're going to set this equal to 0 first, because we've got to set both partials equal to 0 to find the critical points. Then I'm going to replace y with x squared over 4. So this becomes 6 times x squared over 4 squared minus 24x, which will give us x to the 4th over 16. 6 over 16 reduces to 3/8. So we have 0 is 3x to the 4th over 8 minus 24x. We want to solve for x. And then once we get that x, we're going to go ahead and solve for y by using this formula. We've got some more work to do on x here. So let's go ahead and multiply both sides by 8. If I do that, I can get rid of the denominator. So 0 times 8 is just 0. 8 times 3x to the 4th over 8 is just 3x to the 4th. 8 times 24 is 192. So bringing the 192 over to the left side, we have, or factoring, I guess, is better, of course. 0 equals 3x times x cubed minus 64. So 3x is 0, or x cubed minus 64 is 0. Well, if 3x is 0, dividing by 3, we get x is 0. If x cubed minus 64 is 0, I get x cubed is 64, which of course means x is 4. So we have critical points where x is 0 and x is 4, but that's not enough. I also need the y value that goes along with the x of 0 and the x of 4. what did we see earlier? We saw that y was x squared over 4. So I plug the 0 in, 0 squared over 4 is still going to give me 0. If I plug the 4 in, 4 squared is 16. 16 over 4 is 4. So we have found two critical points. We found 0, 0 as a critical point. We found 4, 4 as a critical point. In each case, f sub x and f sub y were equal to 0. Now we want to determine whether these critical points are minimums, maximums, saddle points, or maybe we're unable to tell. So we need a strategy to find that out. We're going to look at the second derivatives. So f sub x, x, that means first take the partial with respect to x, and then take another partial with respect to x of that. So that is the partial with respect to x of f sub x. What we had f sub x up here was 6x squared minus 24y. So we need the partial with respect to x of that, which is the partial of x of the first piece minus the partial of x of the second piece. This has no x. This will be 0. This I can pull the 6 out in front. So 6 times the partial of x squared, which is 6 times 2x. And we get fxx is 12x. That's the second order partial. First with respect to x, second with respect to x. So we'll need to use that. I also need fyy. So that means first take the partial with respect to y, which we have up here, 6y squared minus 4x. Then take another partial with respect to y of that. So partial of y of 6y squared minus 24x, which is the partial of y of the first piece minus the partial of y of the second piece. And again, second piece has no y's. So the partial of y of 24x is 0. We can pull the 6 out here. We can take 6 times the partial of y squared. Now it's just the same as the derivative. So that's 6 times 2y, and f sub y is 12y. We also need the mixed partials. Now f sub xy and f sub yx should be the same. We'll go ahead and do f sub xy. That means first with respect to x, and the second one with respect to y. So the partial with respect to y of 6x squared minus 24y. That's the partial of y of the first piece minus the partial of y of the second piece. This one is 0 because there's no y involved. This one, the 24, comes out in front, and we get 0 minus 24 times the partial with respect to y of y. At this point, it's just the derivative with respect to y of y, which is 1. And we get f sub xy is negative 24. Now, I'm not going to officially do f sub yx, but you see how it's going to be the same thing? If you take the partial with respect to x of this, that'll give you 0. That'll give you negative 24, and the result is the same. In this class, f sub xy and f sub yx will always be the same. Mixed partials will be equal. Now we have all of the mixed partials we need, and we need a classification scheme. We have our critical points. We need to determine whether we have a minimum, a maximum, a saddle point, or maybe the test fails. So here's what we have to use. I call it D. It determines whether the thing is a minimum, a maximum, or a saddle point. D is fxx times fyy minus fxy squared. And here's the strategy. If D is positive and fxx is positive, it's a minimum. Focus on this piece. Think of positive concavity earlier. If we have a situation where the second derivative is positive, we have a minimum by the second derivative test. Same thing holds here. If D is positive but fxx is negative, think of negative concavity. That gives us a maximum. But remember, D has to be positive first. If D is negative, then we have a saddle point. So you think of a saddle, a Pringle potato chip, where it's a maximum from one perspective, it's a minimum from the other. And if D equals 0, the test fails. There's no way for us to determine that using this strategy. Just like in the second derivative test, if D was 0, the test would fail. So here's what we have. We have our original function f of xy, our critical points 0, 0, and 4, 4. And those are our second order partials fxx, fyy, and fxy. So D is fxx times fyy minus fxy squared. So 12x times 12y minus negative 24 squared. Of course, negative 24 squared becomes a positive number. The first piece then is 144xy minus 576. We have to apply that D to each of the critical points to determine if what we have is a minimum, a maximum, a saddle point, or possibly none of the above. So there's our critical point 0, 0, our critical point 4, 4. If I plug 0, 0 in for xy, that gives me 144 times 0 minus 576, which is negative 576. If d is negative, we have a saddle point. So there's a saddle point at 0, 0. If I plug in 4, 4, 144 times 4 times 4 minus 576, 1,728. So d is positive, but that's not enough for us to say if it's a minimum or a maximum. We know there will be one. But now we've got to look at fxx. If d is positive, what is fxx? fxx is 12x. Plug the 4 in for x. fxx is 12 times 4, or 48, which is greater than 0. So you think about a situation where you have positive concavity. When you have positive concavity, indeed, that's a minimum. So we should have a minimum value. But what is the minimum value? Our function was f of xy is 2x cubed plus 2y cubed minus 24xy plus 7. I need to plug the 4, 4 into this to take f of 4, 4 is 2 times 4 cubed plus 2 times 4 cubed minus 24 times 4 times 4 plus 7. That's negative 121. And our conclusion is this function f of xy equals 2x cubed plus 2y cubed minus 24xy plus 7 achieves a relative minimum of negative 121 at the point 4, 4. And that is the conclusion to this question. And that will conclude this lesson.